So we will be talking about an idea of what's called integration. This goes with the idea of antiderivatives. But integration is a little bit more than just an antiderivative. So I want to first start talking about what are called areas and distance. So this is section 5.1 in the textbook. And if you want to find an area, of course, finding an area of a rectangle is just the base times the height. If you want to find the area of a triangle, it's just 1/2 the base times the height because it's half of a rectangle. If you wanted to find an area of a different type of shape, it's not like one of the ones we know. We know other ones like parallelograms and things like that, but we have other shapes we want. And we also know circles and so forth. We want to find this one. To do this, all we would do to find the area of this is think of this as, here I can make it into a rectangle and a triangle. So I have the area 1, which is the rectangle, and the area 2, which is the triangle. I just add the two areas together to get the area I want. So that's not too hard to do. So we know how to do that. We've been doing this for a while. But now let's say I want to find the area of this shape. This is no longer where I can just make it into whatever this shape is. I can't just make it into a triangle and a rectangle because it's not a triangle. It's a weird shape. We have to figure out, how do we find the area of something that's kind of strange like this? And the way we can do this is, first off, we can take and put this on a coordinate plane. So I'm going to put it on a coordinate plane, and then we actually can represent this line up here as some kind of function of y equals f of x, some function. And then we just have a rectangle below it. So we're just trying to find the area of this with that area there. And then what we're going to do to find these is we're going to look at finding that area of that space. We'll call it anything. I would call it A for something better to call it. We want to find that area of that. And we're going to talk about how do we go about doing this. So first I need to know what this function is. Usually that's a modeling process where you go through and model this function. We're going to go ahead and do it for a function we know. So let's take y equals x cubed from x equals 0 to 1. So we know what that function looks like. This is what this function looks like. And this is the area we want. And we want this area here, this area right here. We want to know what this area is equal to. All that. So that's what we're looking for. So we have to figure out how we go about doing that. Well, going back, we know they're rectangles. So what if we were to draw some rectangles in here? So we know we go from 0 to 1. If we went halfway, that'd be 0 to 1/2. If we did half of that, that'd be 0 to 1/4, then 1/4 to 1/2, then 1/2 to 3/4, and 3/4 to 1. And I can think about coming up here till I hit the graph, coming over, and coming down, and there I've made a rectangle. And I can find the area of that rectangle because we know the length of the base is 1/4. We know the height because the height is just a function evaluated at 1/4. So the height of this is just 1/4 to the 3rd power. We can do the same thing here. Come up here from 1/2, come up till we hit the graph, come over with a straight line, and we have another rectangle. And we can find the area of these rectangles because, again, we know the length of the base, that's 1/4. We know the height because that's just 1/2 cubed. Because remember, this function is y equals x cubed. So we just take the x value and cube it, and that gives me my height. Same thing, I can come over here to 3/4, come on up, come over and down, and I've made, again, another rectangle. Again, I know that height is 3/4 cubed. And we can keep going with this. We can come up at the last place, come all the way up from here at 1, come all the way up to where it hits the graph, come over and down, and we can find the area of this rectangle. And of course, the height here is just 1 cubed, or 1, and the area of the base, the length of the base is just 1/4. So we can actually find that and find what that equals. So we can actually take and add all these areas together. We can add up 1/4 cubed times 1/4. That's the area of this first rectangle, plus 1/2 cubed times 1/4. Remember, the length of this base is 1/4, because the difference between 1/2 and 1/4 is 1/4. Plus, then the next rectangle has a height of 3/4 cubed, times, again, the length of the base, which is, again, 1/4. And then plus the last one, which is 1 cubed times 1/4. And we have all these rectangles, and it gives me kind of an idea of what it is. What I do notice is that I got a lot of extra space here. All that space right here, this space right here, I'm going to make a different color here. This space right here, that I know what that area is, and I've got all that space there. And I got to figure out what that is. Well, that's kind of wasted space. It's leftover. And same thing here, I got this wasted space, and I got this wasted space, and this wasted space. So I've overestimated what the area is with these values. Now, one thing is I notice that between 0 and 1/4, I'm using the right endpoint of that interval. And then from the interval from 1/4 to 1/2, I'm using again the right endpoint of that interval. Same thing with this one and this one. So these are known as right endpoints. There's 4 rectangles. So we actually can call this R sub 4 because it's using rectangles and it's using 4. So we're using the right endpoint and we have 4 rectangles. Well, there's no reason why I had to use rights. I could have done the other way. So again, I'm going to use the same picture, same graph. And this time, we're going to again divide our interval from 0 to 1 in half. Divide that in half again, 1/4 and 3/4. But instead of starting over here at 1/4, I'm going to start over here at 0. Well, if I come up from 0, I hit 0. So there's my rectangle. It's just a line. If I come up from 1/4, I come over till I hit the 1/2 and down. There's that. The height of the first rectangle is, of course, 0 cubed because it didn't go anywhere. The height of this rectangle, because we came up the 1/4, this height will be 1/4 cubed. Then from this interval from 1/2 to 3/4, I'm going to come up from the 1/2, come up till I hit the graph over, and again, I get a new rectangle. The height of that rectangle will be 1/2 cubed because I have that endpoint. That's how high I came up. That's my y value. And then if I go from 3/4 to 1, I'm going to come up from this left endpoint up to 3/4 till I hit the graph, come over and down. And the height of that one is 3/4 cubed. And again, I can find the area of all of these rectangles and add them all up. So this would be 0 cubed times 1/4 plus the height of the next rectangle is 1/4 cubed times 1/4 plus the next of the next rectangle has a height of 1/2 cubed times 1/4, and the next rectangle has a height of 3/4 cubed times 1/4. This time I use the left end points of this interval from 0 to 1/2. I use the 0. From 1/4 to 1/2, I use the 1/4. From 1/2 to 3/4, I use the 1/2. And from 3/4 to 1, I use the 3/4. So I always use the left-hand point. And there's 4 rectangles. So this we could call L sub 4. If you want, you could take out your calculator and find out what both these are. So approximately this one is approximately 0.140625. It is probably not approximately. It probably actually is equal because we're using 1/4. The other one, if I went and did this one again using my calculator and just finding out what the values are, this one would equal 0.390625. And so I know that my true area is somewhere between those two values. Notice on this first one, we had overestimate. We were way above what the value was. On this one, we're way below. Notice in this case, there's again some wasted space. This space isn't counted, and this space isn't counted, and this space isn't counted, and this space isn't counted. So in these cases, we have things that are not counted. So this is considered an underestimate. The other one's considered an overestimate, and the true area is somewhere between these two. So my true area is somewhere between these two. We're not exactly sure where, but somewhere between these two is what that true value is. Well, how can we get a better estimate? Well, instead of drawing these each time, I'm going to let technology draw it for me. So I'm going to go and use a Desmos little app that it has. And this Desmos is using where we're going to put in a function. I'm going to change this function was just what was there. I'm going to change my function to x cubed. And then I'm going to put my endpoint, my right endpoint, my left endpoint, sorry, was 0. So I'm going to change my left endpoint to 0. My right endpoint was 1. And then there's what my picture looks like. I'm going to go ahead and we went to having 4 rectangles, and there's what those values were. These are using the left and the right endpoint, sorry, no, the left endpoints. It's using the left endpoints, and there's with 4 of them. So that's the same picture I drew. Notice again, there's extra space here and here, and you can't see the one there. That's right on there. I do see that it actually evaluated down here. It actually gives me what that approximately was equal to. It added those up. This is what this big symbol here means. It means add them all up. So it added up the area of all these rectangles, and we get 0.140625, which is what we found when we did it by hand. If I change this C equals 0 to C equals 1, then it's got my right endpoints. So notice it now has the right endpoints I'm working. Notice again, we have that extra space here. And again, it tells me that's 0.390625. If I went ahead and increased my n to, let's say, 8 endpoints, then it's telling me that that adds up to 0.3164. If I went and changed this down to C equals 0, so it gets my right end, my left end sums, it's 0.191. So I get a little bit better estimate when I made a little bit more rectangles. So if I go back over here, I can put those in. We had gotten with n equals 8. My L sub 8, remember that means left sums, left endpoints, was 191,40625. And my right sums was 0.316, sorry, yeah, 640,625. So I know my area is somewhere between these two. So I can now say my area is now between these. And notice we get a little bit tighter. This is a closer interval than we had before. If you wanted to, by the way, you could actually just average these two to get a little bit better answer. But still, we're not really that close. I'd like to be a little bit closer here. So let's go back to our Desmos. And let's increase the n to, I don't know, let's go up to 20. So when I go to 20, notice there's not as much leftover space. We actually are pretty close to what the values are. We're getting pretty close to right under that curve. There's not a lot of extra space. We get a value of 0.225625. If I went ahead and went over to n equals 1, then notice I don't have a lot of extra space up above. So I'm getting pretty close to the answer. And notice this time I get 0.270625. So we can actually make a table here. So we'll make a little table and we'll put those values in the table. All right, sorry, my table is not moving very well. Okay, there we go. Finally got my table where I wanted it. So we now had n equal to 20. And we'll look at the left sums, call it Ln, and the right sum, Rn. And we had 20, we got 0.2256. 0.25. And then we had the 20, the right-hand sum was 0.270625. I might now increase my n even more. So I'll go back to that Desmos and see what I can increase my n to now. Let's say if I increase my n to, I don't know, let's go up to 50. Notice really there's not a lot of extra space here. This was a right-hand sum. There's not a lot of extra space. It looks like we've got pretty much everything that's under that curve. If I go over to the right-hand sum, the left-hand sums, notice there's not a lot of extra that's left out. So this is really much better. Notice with the left-hand sums, and I'm calling left-hand sums because we're using the left hand of that interval, and we're then going to sum those values up like we did before. And that's 0.2401. The right one was 0.2601. So that's pretty cool, because now what I'm looking at here, when I have n equals 100, I got 0.2401, and I got 0.2601. Notice those are really close. This is looking really good, like I've got a really good value. Let's go just a little bit bigger. Let's say we do, sorry, that was 50. Didn't mean to put 100. Let's do 100. So let's do 100. And we'll see what happens when we do 100. So we'll go back to our Desmos. You can do these by hand, but it's a lot faster doing them this way. 100's all the way over here to the end, so we'll just go there. Now I've got my right-hand sums. Notice you pretty much can't see anything really over. You can see a tiny bit over, so there's a little bit of an overestimate, but not a lot. We get 2.255025 for that value. If I went to the left-hand sums, that means just put your C to 0. Notice there's not a lot missing here. So we get 0.245025. So we can now put those into our chart, into our table. So we had 0.24505, and this one is 0.25525. I could keep going, but unfortunately Desmos doesn't keep going. So I could do this by hand. I could actually keep doing this and make it go even higher and bigger. But what I notice is my left-hand sums seem to be approaching some value. My right-hand sums seem to be approaching some value, and they seem to be approaching the same value. So I can now say that it looks like my sum is around these two, between these two. So I can now go ahead and write that my area is between 0.245 0.25 and 0.255025. If I wanted to, like I said, I could get just a one single estimate by just taking the average of these two. So add these two together and then divide by 2. And when I do that, I get 0.25. So it looks like that area is 0.25. That's what it looks like it might be. I'm not positive that's what it is, but it looks like that limit of the right-hand sums and left-hand sums is the same. So we can just kind of say that it looks like the limit as n gets bigger and bigger and bigger, which means it's going to infinity, of that right-hand sum is 1/4. And also, by the way, the left-hand sum. You might mean to put a 4 there, sorry. It looks like they're both getting to be about 1/4. That's where they look like they're heading. And we've got that now. We can look at it and we can actually kind of prove it is. And we can prove it is by looking at kind of what our sums are we have. So what I want to look at is that if you look at a triangle here, and we're going to go ahead to a new page here, do it this way. It looks like that's what it's doing. That's what it looks like is happening. And what I can do is, again, I can think of dividing this up if I say 1 is n over n, then half of that would be whatever, and we can actually think about having 1 over n a bunch of times. So we could have 1 over n here. This would be 2 over n. This would be 3 over n, and so forth till we get up to n over n. So what it looks like, if we're looking at right-hand sums, it looks like we're adding up 1 over n, which is the length of this, the width of the base, times the height, which is 1 over n cubed, because remember this is x cubed. Plus, then we also have the 1 over n times 2 over n cubed, plus the 1 over n times 3 over n cubed. I'm going to keep doing that till we get up to n over n. So 1 over n, n over n cubed. And notice I didn't write it as 1 because I want to kind of think about kind of a pattern I'm seeing here. One thing as a pattern I noticed is that every single one of these terms has a 1 over n in it, so I can pull that out. The other thing I noticed is that each one of these has an n cubed in the bottom, so I can pull that out. And what I'm left with is 1 cubed, 2 cubed, 3 cubed, all the way up to n cubed. But if I'd written this as 1, I wouldn't have seen that. So this is why it's kind of important not to always simplify things. And this looks like this is what the answer is. So if I could just figure out what this sum is, I'd be in good shape. Well, mathematicians have figured out what that sum is. It turns out that that sum is equal to n times n plus 1 cubed. Sorry, n times n plus 1, can't read my own handwriting, no cube, all over n, all over 2. And this thing is going to be squared. And this is what it comes up to be. So if I wanted to do this, my r sub n, therefore, is equal to, not right now, Sydney. My Rn is actually equal to is equal to 1 over n to the third times n, 1 over n to the third, 1 over n, so it's 1 over n to the fourth, times n plus 1 squared, over 2 squared. And so if we can just find out what that limit is, we're in good shape. If you want to, you can actually make this a little bit easier. This would actually be n squared times n plus 1 squared over 2 squared, which is 4, times n to the fourth. So if we want to find this limit as n goes to big, remember we're going to let n get really, really big. We're going to let n keep going bigger and bigger and bigger, and we saw it got a better and better estimate. So it's the limit as n goes to infinity of n squared times n plus 1 squared over 4 times n to the fourth. If we can find out what this limit is, we would know what the answer is. Well, the 1/4 can come out, so we'll bring that out. The rest of this can't because it all involves n's. So we've got n squared over n to the fourth is n to the fourth in the bottom, so 1 over n squared over n squared. And then we just figure out what this is. And you can actually use L'Hopital's rule here because you've got infinity over infinity. So you can use L'Hopital's rule. L'Hopital's rule would say that this would be, using L'Hopital's rule, we've got 2 times n plus 1 times 1, because you're doing the chain rule. So you take the derivative of the outside, which is 2 times something to the first, times the derivative of something, but the derivative of n is 1, over 2 times n. Again, you still have infinity over infinity, so we have to do L'Hopital's rule again. That will give me 2 in the top over 2 in the bottom. So that's the limit of 1, and the limit of 1, of course, is 1. So we get 1/4, which is kind of what we thought it was, and it seemed like it was looking towards that. Similarly, the limit as n goes to infinity of L sub n would also be 1/4. So that tells me that my area is the limit as n goes to infinity of my right-hand sums. It's also the limit as n goes to infinity of my left-hand sums, and they should go to the exact same value. And we know now that that's equal to 1/4. Let's look at a general region and what's happening, just to get an idea of what's going on. So again, what we're going to do is we're going to divide this interval from A to B up into so many what we call sub-rectangles. So the first thing is to figure out what that is. So let's say we want n rectangles, and that means we're going to divide this interval from A to B by n. Now tell us what our change in x is. So our change in x is b minus a, the length of this interval, divided by how many rectangles I want. X sub 0 is a. X sub 1 would be right here. X sub 2 would be right here, and so forth. Well, x sub 1 is equal to x sub 0 plus delta x. X sub 2 would be x sub 1 plus delta x, and so forth. And so that means that my x sub I, any x here, anywhere in this interval, would be equal to x sub I minus 1, the one right before it, plus that delta x. And then we can either do left or right sums. It doesn't really matter which ones you do. So we come up from the right, come over and down, then come up from the right till you hit the graph, come over and down. Here again, we're going to have, let's put an x to I minus 1 in here. We're going to come up till we hit the graph, come over and down. And then all you do is find out what the function values are at each of these heights. And you keep going. In this case, you keep going till you're down to x to the n minus 1, because this is xn. You come up here, over and down. And you have a bunch of these in between. So dots in between. You have a bunch of these you're going to draw. You have all these different regions, and you can just add them all together. You could have also done the left-hand sums. It doesn't really matter which ones you do. That's what you would do. And of course, the height of each of these is just the function evaluated at the x value. So this would be the function evaluated at xi. This would be the function evaluated at x2. This would be the function evaluated at xn, and so forth. Same with the other ones. And so what that gets me, I could do the exact same thing with the other sides. And that gets me, well, let's write it down so you can see what it gets me. Get rid of this one. Oh. That would get me my area is the limit as n goes to infinity of my right-hand sums, r sub n. Kitty, go. Sorry, my cat was on me. All right. Sorry for the delay here. All right. Okay, so this would be the limit of r sub n, and that would be the limit as n goes to infinity of f of x sub 1 times delta x, because again, the base is delta x. That's what that distance is. And then plus f of x sub 2, which would be the height, times delta x. And then you keep doing that. You can even think about getting to x sub I there all the way to the end. And so you'd have f of x sub n times delta x. And so that's what your limit would be, and that's what your area would be. And again, we can do the exact same thing with the left-hand sums. I could come up here. My delta x is still the same. So I still would have a delta x. My delta x is still b minus a over n. So that's still what it is. It doesn't change just because we're using left-hand sums. But now I come up from the left, At x0, come over and then down. Come up here till I get to the top. Get to the top of the, hit the graph, come over and then down. Come up here till I come over and then down. And again, you'd have your x of I somewhere here in the middle. In this case, you'd have x of I as your left-hand point, and then x of I plus 1, and so forth, all the way up here to x of n, and minus 1. And you come over here, and you come down. So there's those, and again, your same functions. Your heights are still the same. The height of this function here would be f of x sub 2, because you used the right endpoint and that right endpoint, sorry, left endpoint, and that left endpoint is x sub 2. And again, you could find that area. Your area would be equal to the limit as n goes to infinity of those left-hand sums. And that would be the limit as n goes to infinity. You'd, in this case, start at f of x sub 0. Notice the last one started at x sub 1 because you were using right endpoints. This time we're using left endpoints. So you start at x0 times delta x, then f of x1 times delta x. Keep doing that till you get to f of x n minus 1 times delta x. So your left-hand sum start at x0 and end at x of n minus 1. Your right-hand sums start at x1 and go to x of n because of the sums they're doing. Okay, we don't have to use just the left-hand points and right-hand points. You can use any points you want in that interval. It doesn't matter which ones you use. So you can use either one. It's really any point you want. So it's just really always going to be f of x I x1 star delta x plus f of x2 star delta x all the way through to f of x n star delta x, where x I star is just some point in their interval. So we actually can think of this as x of I star is some point in the interval in the I minus 1 to I interval. This is really long to write, and we get really bothersome writing this. So we actually have this notation here. This is called the summation notation. This is the Greek letter epsilon, capital sigma. Gotta get my right. This is capital sigma. I equals 1 to n means that we're starting at 1 and going to n. Of my function, each of these terms is f of x sub I star times delta x. So every single term is involving an f of x sub something star times delta x. And then the I equals 1 means you start at 1, go to 2, go to 3, all the way up to the n at the top. So using this notation, a is equal to the limit as n goes to infinity of r sub n. That's the limit as n goes to infinity of the summation I equals 1 to n of f of xi delta x. We want to do the same thing with the left-hand sums, but unfortunately they started at 0. So we actually will start the I at 0. You can change these summation symbols, these indices, anything you want if you need to. And this one we want to start at 0. It goes to n minus 1. You could also, by the way, have started this at 1 and gone to n and made these I minus 1, and that would have been fine too. It's really up to you. So you could have done either way. It would have been the same thing. And then my area is just the limit as n goes to infinity of that summation of any point. So again, I can use midpoints or any point I want. Desmos actually allows you to use midpoints. 0, use c equals 0 for left endpoints. You use c equals 1 for right endpoints. And you use c for half to get those midpoints. And just to show you kind of what that looks like, I'm going to make get to 4 intervals here. And in this case, this is the halfway point between 0.5 and 0. That would be that point right there. Notice it came up and went over. Then this is that halfway point between 0.5. This is a quarter. So this is a quarter, and this is halfway between a quarter and 0.5. This is halfway between a 0.5 and 3/4. And this is halfway between 3/4 and 1. So that's all it was doing there. Okay. So we can actually do the same thing using the right endpoints and midpoints using with 4 points, we can find out what the area is under e to the negative x squared from -2 to 2. We will actually use the Desmos for this. So I'm going to go back into Desmos. I'm going to change my function. I changed my function to x cubed. I'm going to change my function now to e to the negative x squared. And I want to change my left endpoint to -1. No, I'm sorry, -2, I believe I said. Yes, -2. So A is your left endpoint. Notice we're now coming down here to -2. My right endpoint, I want it to be 2. So I'm going to move B to 2. That's my right endpoint. If you forget these things, it says left endpoint and right endpoint right there. And notice we get this interesting looking curve. For those of you who have taken statistics, this is actually known as the normal curve. It's a little slightly different from the normal curve, but it's close to that normal curve. The reason I say slightly different is because, well, actually, no, this is the standard normal curve. So we're good. I think there's a pi missing somewhere here, but it's close enough to what it would look like. And we want to find the area under this curve. And we do this a lot in statistics. We want to find this out. I said I wanted to do left endpoints and midpoints with 4 rectangles. So I'm going to do the left endpoints. I think I said right endpoints. So I want to do the right endpoints. So I'll send C equal to 1 for right endpoints. So notice it's doing the right endpoints. So again, from this interval from 1 to 2, we only had 4. So we're going from -2 to 2. So that length of that interval is 4. We want 4 intervals. So we divide 4 by 4 gives me 1. So that's why my rectangles are all length of 1. This length rectangle goes from 1 to 2, and we come up from the right end point, come up from 2, over and down. At 1, we come up, over and down, and so forth. Notice there's a lot of empty space, but there's a lot of open space over here. And you can come down here and you can read what that is. Notice we now know what that summation notation is about. So this is using that same notation that we were just looking at. There's the function being evaluated at my point and times the width of the interval, and then we're adding those all up. And we get 1.754. So obviously there is something missing in this. This is not actually the normal curve, but it's close to the shape of it. And then if we want to do midpoints, we said C equal to 0.5. And again, that means that the midpoint between 1 and 2 is 1.5. We come up from 1.5, we draw and down. Come up from 0 to 1, the midpoint is 0.5, so we come up, over and down. The midpoint from -1 to 0 is -0.5. We come up, draw a rectangle at that height and down. And then from -1 to -2, the midpoint is -1/2. Come up till you hit the graph, and there's your height of your rectangle. And we add these all up. Notice there's not as much missing on these when we do that. So that's sometimes why people like the midpoints. It gives a slightly better information. And there's your value. And we can get that and put that in. All right, so we just did that. And we can also estimate distances with this, not just areas. So I did want to mention that we did start talking about distances. We didn't do much with distances. I mentioned it at the start. I want to show you how we can do it. So what I did was I actually was traveling to Phoenix one time, and during a period from 0 to about half an hour, I measured what my speed was. So that wasn't time 0 when I left. It was just what time period I started measuring. And at time 0, my velocity, actually this is speed, but we'll go with velocity at the moment, was 75 miles per hour. A tenth of an hour later, it was 80 miles an hour. 2/10 of an hour later, it was 78 miles an hour. 3/10 of an hour later, it was 65 miles an hour. Probably went up a hill. Another tenth of a mile later, it was 70, and then another tenth of a mile of 78. And what I like to do is what was my distance I traveled during this time period. So we're going to use left-hand sums and right-hand sums. I'm not going to use midpoints because I don't have the midpoint values. So we'll first do left-hand sums. I don't know what my n is going to be, so I just call it L. The reason I say that is because I already have my delta t in this case. My delta t is 0.1 because because I went from 0 to 0.1, 0.1 to 0.2, 0.2 to 0.3, 0.3 to 0.4, 0.4 to 0.5. So I know what my delta t was, and my L therefore will be my velocity at that point. Call it T sub I times delta T. I'm going to add those all up. So we're going to add those up. I didn't put my notation on here. I'm just reminding myself I'm adding things together. So I just left it off in this case. We're using left endpoints. So left endpoints means between the interval from 0 to 0.1, we're using the 0. So the very first one there would be 75 times my delta t of 0.1. So let's write delta t equals 0.1 up here, just so you can remember. Not 0.01, 0.1. And the reason it's 0.1 is because that's how often I measured. No other reason. I could have measured more often, but I only measured every 0.1. So my delta t is 0.1. Your delta t is whatever, if you have a table like this, your delta t is whatever that separation is between the different values. Occasionally, these can change. So your delta t may not always be the same value. So in that case, you'd figure out what the delta t is between each one and find out what that is and multiply by that delta t. In most cases, they're usually the same. So we have 75 times 0.1. That's my first left endpoint. My next interval is from 80 to 80, from 0.1 to 0.2. We're going to use the 0.1. So we're going to have 80 times my 0.1. So remember, this is areas of rectangles. So this is the height times the base. Height times the base. So the next interval is from 0.2 to 0.3. That's going to be the 78 times 0.1. The next interval is from 0.3 to 0.4. That's going to be the 78. That's going to be the 65 to 70, sorry. So that's the 65 times 0.1. And then the last interval is going to be this last space here, 0.1 to 0.04, 0.4 to 0.5, sorry. And that's going to be the 70. And then we just have to add those up and find out what that is and figure out what values we get there. I was hoping I'd already added it up because I don't have a calculator with me. But you can just add those up. You know how to do that. I'm sure you know how to add together numbers. I can also do the right-hand sums. So we'll do the right-hand sums. The right-hand sums means I'm using the right end of that endpoint. So my first endpoint is from 0 to 0.1. So I'm going to use the 80 as my right-hand point of that interval. From that interval, my right-hand point is the 0.1 or the 80. So that's going to be the 80 times 0.1. Then the next interval would be from 0.1 to 0.2. That will be the 78 is the right endpoint. So 78 times again 0.01, not 0.01, 0.1. The next one would be the 0.2 to 0.3. That right endpoint is the 0.3 and the 65. So it'd be 65 times 0.1. The next one is 0.3 to 0.4. The right endpoint is the 0.470. So it'd be 70 times 0.1. And then the last interval is from 70 to 78. It's the 0.4 to 0.5. So the right endpoint is 0.578. So you can add these all up and find out what your total distance is. I'm going to go ahead and get my calculator and do that just so you can see what values we have. So 75, and notice that each one of these is being multiplied by 0.1. So I can actually just add the numbers together and then multiply by 0.1 in the end. That would probably be a little bit faster. So this first one is 36. No, I can't do that. $36.8. Now, these are in miles per hour, and these are in 1/10 of an hour. So notice my time was in hours, and this is in miles per hour. So miles per hour times hour gives me miles. Make sure they're the same units. If this was miles per hour, but this was minutes, then you'd have to change your minutes into hours or your miles per hour into minutes, miles per minute. So make sure these are the same units, because what is happening here is we have miles per hour times hours, and the hours will cancel. So make sure that you've got the same units going on here so that those can cancel and you'll be left with miles. This one here, again, I add up the numbers first and then multiply by 0.1. And I get 37.1 miles. So in this time frame where I was measuring this, I went around between 36.8 to 37.1. So about 37 miles in this time period. And so you can always find distance doing the exact same thing.